thanks GCPO for hosting this webinar. And what I want to present on today is the project we just recently wrapped up for the Gulf Coastal Plains and Ozarks LCC, and that was trying to integrate dynamic landscape population models with structured decision making. And let me start off this talk by giving a little bit of information and background on why we would want to do this anyway. What's the reason for this integration? And so to do that, let me start out by introducing you to the Gulf Coastal Plains and Ozarks LCC. You can see that highlighted in the map below. The mission of the GCPO is to define, design, and deliver landscapes capable of sustaining natural and cultural resources at desired levels now and into the future. Please pick up on my sarcasm when I say that doesn't sound like a difficult task at all. Truly, to do that kind of work at such a scale is quite a task. Fortunately, there's this paradigm, strategic habitat conservation, that the LCCs are using, which essentially lets them coordinate various programs and actions across partners and sites so that they can get a combined effect that achieves a desired outcome at that scale. So that's really great for the delivery. They have access to private land funds, access to partnering agencies that can manage the landscape on their own lands, and so they have definitely the ability to deliver these landscapes. That just leaves the difficulty associated with designing these landscapes and making plans and decisions about how to do that. And there certainly are difficulties associated with that. Let me give you an example then for the GCPO. What I'm showing right now is the Ozark Highlands region. It's a subgeography of the Gulf Coastal Plains and Ozarks LCC. And since 2012, the GCPO has been partnering with a team of planners from this region to pilot a process for landscape conservation design. The goal of this team has been to design landscapes capable of sustaining healthy and plant animal communities in the Ozark Highlands. Now, this process that they're piloting is essentially the precursor to what most LCCs now are describing as their blueprints. But essentially, it's a landscape conservation design process. Okay, so on this team, this Ozark Highlands team, you have all the people that you would want on a planning team like this for a regional team. You have Todd and Christine and Jane, who are coordinators for the GCPO and the Central Hardwoods Joint Venture, both regional partnerships. You have Allison and Mark and Nate, who are the habitat coordinators or SWAP coordinators for the 3 states that are part of this region, Arkansas, Oklahoma, and Missouri. And then you have some other expertise like Shay and Esther, who are ecologists with the U.S. Fish and Wildlife Service and the U.S. Geological Survey. And Philip is a biologist with the Missouri Resource Assessment Project to provide some spatial expertise. So you've got a great team that's put together to try to do this landscape design process. And I introduce you to these folks in this team because this is the team that I worked with for this project. We essentially continued on with their work as we brought in our project. So this team then took an ecosystem-based approach to their landscape design. And so by ecosystem-based approach, I mean they focused on restoring habitat systems that should potentially be there in the Ozark Highlands. And you can see this graph below that shows those different habitats. And what they did was they prioritized areas to work in the Ozark Highlands for these different habitat systems based off on an objective, transparent rule set. So they're trying to be objective and say, what are the priority areas we have? And you can see an example of some of these questions that they used in determining the priority of the landscape for restoration. And so they went through this process, they identified these priority areas, and you can see those outlined in the map there. And so when we look at all those areas together then, and you can see those areas in green here, these are the team, what they've identified as the priority areas for the Ozark Highlands in terms of restoration and conservation. Now, it's no exaggeration to say that they're probably not going to be able to restore all of those areas, much less at once. So what happens then is the team is faced with a decision then for how to do landscape conservation design. And that decision really comes down to how are they going to start restoring these landscapes? What is going to be the plan or the scenario for restoration? And are they going to be able, is that plan or scenario going to be able to get them to a sustainable landscape like they addressed in their mission? Well, that you can imagine sitting here looking at all those areas and thinking about where to start, and it becomes incredibly difficult. And it's made even more difficult when you start adding in all the complexities and the problems that can start to happen with planning at this scale. And that is things associated with predicting the future. How do we know what the landscape's going to look like in the future from urbanization or climate change? And how will that affect the effectiveness of our scenarios in terms of restoration? And even for restoration, the what, when, and where, putting those scenarios together is incredibly complex as well. And then you've got, the problem was associated with if under an ecosystem-based approach, you're addressing multiple species. So how are you going to identify the best scenario when there's, different interests from different species? And so if you allow me for a second, what I'm going to try to do is I'm going to try to distill down these kinds of issues into two basic problems or difficulties that regional planning often faces. And by distilling them down and giving them a name, I think it helps us to kind of better target them and address them. And so what I would say is that these issues all kind of fall into two different areas of difficulty. And that is that they are wicked problems and that they're facing what's called a planner's paradox. Okay, let me start with the planner's paradox. And what that says basically is if you're trying to translate regional goals down into local actions, you first need to understand how those local actions are going to, relate to the regional goals. And there is the paradox, because we often don't have that ability to predict that. And so what the planner's paradox is getting at in general is just that it's difficult to predict responses of wildlife or populations of species to different kinds of impacts, whether it be climate change or conservation. And so that's one area of difficulty. The other area is this idea that these are really wicked problems. And what I mean by that is they're extremely complex. We have any number of scenarios or possibilities that we could use to look at, to try, but their future is uncertain, right? We're uncertain about what kind of climate change might occur actually in the landscape. And so the effectiveness of any given scenario is going to be dependent on what the future holds. And at the same time, I mentioned that we've got these competing objectives. We've got different species responding to different scenarios. So how do you identify one scenario that's best when there's competing objectives? How do we resolve those trade-offs? And so these are really two big issues that I think lots of regional planners grapple with: wicked problems and the planner's paradox. Fortunately, and where this project comes in is that there are two emerging areas of conservation science I think can directly address these issues. And the first one is dynamic landscape population modeling. And this is something that Frank and Josh and I, my collaborators on this, have been putting together or developing over the last few years, this dynamic landscape modeling approach. And really what this approach is if you look at the graph here, is we have landscapes on the left, and what we're doing here in this approach is we're linking local habitat and landscape through demographics and a population model, ultimately to produce projections or predict regional growth based on the landscape. And this approach is really important, I think, for two reasons. The first reason is that by linking local habitat with regional population growth, we're essentially capturing the processes that regional populations depend on at all scales. And that is from the very local habitat of whether something's an ag field or a woodland, and how that determines whether a certain species of bird will put a territory in that particular spot in the map. Then we have processes at an intermediate scale like the surrounding landscape and so on that might determine how well that bird's territory and that nest is successful. And ultimately, the demographics that go on throughout the landscape interact throughout a larger region through dispersal and sort of sinks to ultimately drive regional population growth. And so if you're concerned about the regional population, ultimately you need to really capture all the processes that occur along the way. And another reason that this particular approach is important is because it's based off of the landscape. It's based off of maps and local habitat and landscape. Then we have the ability to go back into these maps and this landscape and to simulate changes either from conservation or other threats like climate change or urbanization or so on. We can simulate those changes, and we can reproject and predict what the response of the population will be to those changes in the landscape. And we can do so over time. And so that really gives people, especially planners, the power to start to do those what-if scenarios, and it really allows them to start to evaluate their scenarios that they might want to consider for conserving landscapes. Now, these models give you a nice response. They allow you to predict the responses of the populations to these changes. But that's all they do. They still don't help you with all the other aspects and complexities of those wicked problems in terms of the decisions. And that's where the other area that's seen a lot of use in recent years is structured decision making. I only have one graph here to introduce you to structured decision making, but I can tell you that there's a wealth of information to it. The National Conservation Training Center and the Fish and Wildlife Service provide week-long workshops on structured decision making. So there's obviously a lot that goes into it. It's an overall process, and it certainly has a lot of tools and theory that go into it. But I like this quote because it best captures it in my mind. And what it is structured decision making is a formalization of common sense for decision problems which are too complex for informal use of common sense. So basically what we're doing here is we're breaking down a problem into components, and we can address those components one by one in a common sense way, but it's transparent and it's formal. And so that's why when you have a decision that's highly complicated, if you use structured decision making, hopefully you can start to get at your decisions in a more, in a better way, in a more efficient way. And so that brings me to this project then, what we're doing here. And the idea is that we're going to integrate these dynamic landscape models with structured decision making to help the Ozark Highlands team choose scenarios that best meet and secure wildlife species in the Ozark Highlands. And we're going to do so under climate change. That was a key factor. So that's what we're doing. And really there are three additional kinds of goals that we want to get out of this whole process. We want to be able to first to evaluate the team's landscape design process. So we're hoping that the results we see will give us some indication of whether their landscape conservation design that they did in their priority areas are effective at, if we restored those, they would be effective at sustaining wildlife. Secondly, we want to evaluate this integration between the models and structured decision making and see, does it really help in making these kinds of conservation decisions? And finally, because this is kind of a pilot project, we want to prototype this process. And we want to say, if we're going to turn around and use these kinds of population models and integrate them with structured decision making, what can we do in the next go-around to improve the use of this approach? Can we use it differently, or do we need to make some changes? And so those are three extra goals that we'd like to discuss and see what we get out of this project. So let's jump right into the project then. This occurred over the past year. And what we did is we essentially took the Ozark Highlands team through the PROACT process, which is a subset of structured decision making. And what the PROACT process does is essentially breaks down your problem or your decision into components. First, you identify what the actual problem is, or what you're trying to do. And in doing so, the objectives become apparent, and so you're actually able to list out what are your explicit objectives. Then we have a team describe the scenarios and alternatives that they would try to meet those objectives. And then there needs to be some way to evaluate those scenarios and the consequences of those scenarios in terms of the objectives. And then once you've done that, there's obviously going to be trade-offs and conflicts, and so you're going to need to find a way to resolve that and optimize what decision is best. And so with this process, what we tried to do is take all of those difficulties that we listed earlier, and we tried to place them where they go in this process. And this is really helpful because now we start to pull apart those different difficulties that seem to overwhelm us in the beginning, and now we can put them where they go and kind of address them one by one. And the first, let's talk about objectives. And that's where we start to say, okay, the Ozark Highlands team wants to conserve and sustain species, so species probably should be the objective in terms of sustaining their populations. And so we can acknowledge that they'll go there. And so we had the team identify species that they wanted to focus on when evaluating restoration scenarios. Then we had the team put together alternative conservation or restoration scenarios. And this is where they dug into the what, when, and where. How much restoration do they do? Where is it at? And over how long, and so on. And we needed some specific scenarios here, so the team generated those. What I bring to this process is the dynamic landscape population models down here, and the ability of those models to incorporate the effects of climate change on the region's forest. We also bring in urbanization models and those projections to basically give a backdrop for what our conservation scenarios will be simulated on. So we're going to incorporate all the changes that will happen in the future in the landscape, and then we'll overlay the conservation scenarios on that, and then we can use our models to evaluate the consequences of the responses of the different species to that. There's obviously going to be some trade-offs or conflicts, and there's going to be some uncertainty we have to deal with, and that's where we use the structured decision-making analysis toolkit, which essentially is just some tools and just theory that allow us to kind of get past these complexities to make a decision. So let's step through that in the next few slides to show you the methods that actually went on in this process. And so first, we had a workshop early last year to identify where the team identified species that they wanted to focus on. And because this is an ecosystem-based approach and we were focused on restoring habitats, the team decided to choose species that reflected those habitats. So in other words, if the species responded well to our conservation scenario, that means we did a good job of restoring that habitat. And so we broke those habitats down into 6 different areas, and the team identified candidate species for each of those habitats. And these often were species that were of conservation concern, and species, we also tried to make sure we captured a range of taxa and not just birds. And so you can see these species below. We've got the prothonotary warbler for the floodplains, wood thrush and cerulean warbler for the forest, prairie warbler and collared lizards for the glades and open closed woodlands. And then the team actually decided to try for an Ozark big-eared bat model for the closed oak woodland, but the data just weren't there to model that species, and so we actually ended up creating a kind of a generic biota species. And then finally, the brown-headed nuthatch for open pine woodland. And the reason these species were picked was after the team identified the candidates, it was up to me to kind of identify which of those candidates could I actually model. Where were the habitat models available? What kind of demographic data were available in order to develop the models to evaluate those scenarios? And so that's ultimately how we came at the final set of species here. So those were the objectives, and we wanted to sustain those species. And so for those objectives, we need some type of metric. How do we know if we're sustaining the species? And there's 3 that are often used in planning. The first one is carrying capacity and how it's derived from habitat. So if you're putting habitat out there, you should be increasing carrying capacity, right? Another one that's used is population abundance, right? If we can predict population growth or abundance over time as a result of these scenarios. And then finally, risk of decline. And I'll tell you that I strongly advocated to the team that this be the metric that we focus on, and that's viability, or the idea of risk of decline. And the reason is because we've done some work and we've proven that, first of all, habitat is great. It gives you an indication of whether there's habitat on the ground or not. But we've seen evidence of the fact that adage, if you build it, they will come, is not always true. A lot of species tend to be limited. Their populations are limited by processes other than just habitat. So even though if you put a habitat on the ground, that species may not respond. Okay, so that may not be a good metric we want to use, but we still consider it. Also, when it comes to population abundance, we've also got evidence to show that population size and viability do not go hand in hand. There, you can have a population that is quite abundant, but because of the nature of its demographics and the ecology, it's highly variable, and as a result, there could be some risk associated with decline in the future. At the same time, you can have a species that isn't very abundant in your region, but because that species is stable and their habitat tends to be there potentially, even though there's low population size, they can be quite viable. So we tended to focus on risk and viability metrics for this project. And so let's step to the next step here, and that's alternatives. And this is where I asked the team to come up with some scenarios, or if they had any scenarios in mind for how they wanted to proceed in restoring these habitats. And the team really didn't have any preconceived ideas or no ideas about how they wanted to restore this region. And so with that, the team decided to take a more systematic or structured approach where they would structure scenarios around important issues that they continually grapple with. And the first one obviously is very important, and that's just how much restoration do we need to do. Okay, so we looked at that. And over here in the schematic, you can see the breakdown of the conservation scenarios. And the first one here is the amount of restoration. And here the team chose the central hardwoods bird population objective acreage targets. And so what that was is that the Central Hardwoods Joint Venture has done some work to identify what acres are needed to meet their population objectives. So we thought that would be a good starting point to look at those acreage targets for the same habitats. We also considered what if we only did 50% of those targets, of those acreages for those habitats. And then finally, we considered a baseline run where we restored no acres. So this would essentially, no conservation is done. And this provides our evaluation of, is it even effective to restore habitats for these populations? So this is kind of a baseline control. The next question that the team broke out scenarios around was, how do we prioritize where that restoration occurs? If you remember, they already prioritized much of the landscape and identified areas to restore, but they needed to find out, how do we prioritize the areas within those larger set to actually start focusing restoration on, at the start of it, but also through the next, we can't restore all of it, so how do we proceed with restoration? The first approach was to use the prioritization rankings that they already gave those areas that I showed you. Okay, those prioritizations are based off the current landscape of what they see now, and that's shown here in these couple scenarios. But the team also realized that we're getting ready to model the future landscapes too, right? We're working in climate change and urbanization into these future landscapes. So why don't we just use that information in those models and maps to look at what the landscape will be like in the future, and will that change our prioritization if we knew what things were going to look like in the future? So essentially they reprioritize their design process based off future maps, okay? And so we considered whether that was a better, comparison. And then finally, the team noted the importance of kind of getting some confirmation on the idea of protected lands, managing on protected lands, or restoring protected lands versus focusing on both private and protected lands. And we see these scenarios out here for each of these different prioritizations. Then we have a couple protected versus private and protected. And the reason we do this is because there are some differences here. Obviously, protected lands are public lands that often can be managed directly by the agencies, and they can tend to restore how they will. Private lands, on the other hand, you have to rely on private land enrollment and private land programs to kind of get at the restoration that you might want. So there's some differences there. And so we simulated these different scenarios. Just to give you some specifics, here's the central hardwoods habitat objectives that we were talking about. And you can see these habitat objectives are broken out by the habitat systems. And in total, the full acreage objectives that we targeted were almost 3 million acres of habitat across the Ozark Highlands region over time. Okay. Now, just to discuss it for a second, the prioritization, I mentioned that the two different ways we considered to prioritize where we were going to restore habitats were on the current landscape and then reprioritize based off future landscapes. And again, I want to mention that we're incorporating urbanization here from the SLUT urbanization model projections. And we're also incorporating climate change impacts on the forest and based off the land use projections. And I'll cover some of this in more detail here in a minute. And then finally, we looked at protected status or ownership. In other words, protected areas or restoring on both private and protected areas. And just a few housekeeping things here, just so you know. When we went to simulate these different scenarios, we tried to do so in as a realistic manner as possible. For example, actual restoration over time occurred at the patch scale. So we were selecting patches across this landscape within the different priority areas. Those patches that we restored were randomly picked within a certain priority class. So we would prioritize where we were doing, what areas of the landscape or region we were going to focus on, but within there, we randomly selected patches. This kind of gets at the opportunistic nature of how restoration typically occurs today. Even though we ran these simulations through 2100, we actually implemented the restoration only over the first 50 years, so from 2010 to 2060. And the reason we did this is because we wanted to, we wanted a time period after the restoration to be able to let the populations respond to the activities and see how they would respond. And so here's a graph that shows you how we implemented restoration in terms of the number of acres over time in those full acreage scenarios. And so you can see here that we start in 2010 and we restore habitats proportionally through 2050. So in other words, we're selecting patches over the first 50 years to restore habitats until we meet their acreage targets. And at that point, then we kind of hold those constant. Okay. Here are some maps that illustrate what that restoration actually looked like in a map. And so you can see here across these maps, the cells or the lands in green are public lands that end up being restored. The lands in orange are the private lands that end up being restored over time under this particular scenario, which was the full acreage targets on both private and protected lands based on the current landscape. And you can see that increase in color that shows you that the increase in restoration across the landscape. And you can see that by 2060, that kind of stays the same then. Okay, and so these areas in color are the areas that are going to be restored in our simulations. Here's a side-by-side comparison of what the restoration restored areas look like in 2100 under full acreage. And on the left, we have just protected lands. And on the right, we have private and protected lands. And I should note at this point that what we realized in these scenarios is that we're limited in the number of acres of restoration that could occur on protected lands because there's just a limited number of public lands out here. And by protected lands and public lands, I mean national forests, conservation areas, nature conservancy areas, and so on. And so we were limited here, and there was less acres in these scenarios than there were in the private and protected, which is, it's something that makes sense, but it was important to realize that from a planning standpoint. So once we've identified those areas to restore, then we have to simulate the changes that are going to happen from our restoration, right? And so what we do, if we took those areas that you saw in the previous maps, and we said we're going to identify those areas in every decade where the restored and unrestored lands are, then we're going to say in each of those decades, then any restored lands get the conditions that we've already mapped out that we know we want for those different habitats. So each habitat has an associated land cover, canopy cover, and associated forest conditions that we're going to manage for. Therefore, those restored lands in each decade are going to get that. Conversely, if anything's unrestored in this time period, what we're doing is overlaying the conditions that we would have predicted based on climate change and urbanization. Okay, so you can see how the landscape will change over time based off of what we're restoring and when versus what's projected to happen in the background anyway from climate change and urbanization. And so let me go back for just a second. What those conditions are, I mentioned lands cover and canopy cover. These can really be any conditions that we simulate. And what determines what conditions we simulate are what conditions are needed for the species habitat models and population models. Okay, so we're essentially modeling the habitats now for these species. And that brings us to then the idea of these dynamic landscape models and how we bring in climate change projections and urbanization and overlay the scenarios and ultimately evaluate them. And so let's talk about that for a second. We're evaluating simulation across the backdrop of climate change on the forest. Okay, and so it's important to talk for just a second about how we arrived at these projections of what the forest will look like in the future under climate change. And this is where Frank Thompson and his collaborators here at the University of Missouri have put together this modeling approach to project changes in landscapes and forests over time under climate change. And what they do is they combine population or climate models with data such as temperature and precipitation. They integrate that information into an ecosystem model that essentially combines soil characteristics and vital rates of different tree species and so on to identify the ability to establish and grow of each of those tree species over time. And so as those tree establishment and growth probabilities start to change for different species over time, that's integrated into a Landis model that includes other natural succession processes and landscape processes that are important for forest over time, such as seed dispersal, shade tolerance, mortality, and then disturbance and harvest management. So all those processes are captured along the way, and what you ultimately get are information on forest conditions mapped out over time. These conditions, include basal area, tree density, stocking, canopy cover, anything that we can derive from these forest models. And we do so for different species over time. That provides the basis then for the habitat models. And just to give you a quick example of what we're looking at here, this is the larger central hardwoods region. The Ozark Highlands is really this kind of portion here. And this is what the Landis models project for white oak under severe climate change and moderate climate change in terms of its distribution over time at the 300-year mark. And what you can see is that in 300 years out, we start to see some extinction of white oak in the southern portions of the Ozark Highlands. Less so in the moderate scenario. But I should point out here that this is 300 years out. We're relying on projections just 100 years out. In all reality, the models don't show a ton of change or nothing this drastic within the next 100 years. Okay? So that's something to keep in mind. So once we've generated those landscapes then from Landis that account for climate change, and then we've also burned in urbanization as well, we take those landscape models and we put them into the dynamic landscape model that you see here. And this is really messy, and I apologize, but what I'm trying to show you here is that this is a quantitative model. There are a lot of quantitative population ecology kinds of processes going on. And so it's a valid model, and it's quite complex in the ability to capture those. But when it comes down to it, what we need to be concerned with is just that what we're doing here is we're just taking climate and landscape models and how they're mapped across the region, and we're translating those into using habitat models to estimate the demographics such as reproduction and abundance and dispersal of these populations over time. And once we have those estimates of demographics over time, they all feed into a population model over here that we can project population growth of the whole region over time. And what that looks like, and let me give you just a brief touch on what these habitat models are. So for example, to estimate abundance, then we would rely on something like a multi-scale habitat suitability model that's generated for these regions. And they're species-specific models, and they key in on different habitat characteristics and how that helps improve habitat for a different species. And so you can see some of the relationships here that might be captured in those models. Ultimately, we take these and we use these to estimate then abundance or carrying capacities for different species over time. And so all that goes into the model, then, and what we get is we get estimates of population growth over time for the region, but we get a bunch of these different estimates, and that's because we've incorporated uncertainty and variation and stochasticity into the model. And we do that on purpose because we want to kind of account for the fact that we're uncertain about a lot of this process. We're uncertain about survival rates and reproduction and so on. And so purposely adding in this uncertainty and stochasticity accounts for that uncertainty. And so now we get a bunch of runs that could do any different number of things. But at least what we can do now is we can distill that down into an average projection as well as some error or uncertainty around it. And this is what we're then able to base our evaluations on, and we can look at how species respond or their populations respond to climate scenarios. Now, this is a good point here at this point to, if the organizers want to bring up that poll that we'll ask you in the audience to answer. I go ahead and invite the organizer to do that now.
Hi, this is Yvonne. I'll be launching the poll, so hopefully this works. Let launch that now. So the question that Tom would like to propose to you to just get some feedback for informing how useful this information is to you. First question is, which best describes your attitude about the landscape, habitat, and wildlife modeling that is covered in this project? So if you could just go ahead and select one of those answers for this poll, and we'll give you a couple minutes here to answer that one. And just so you know, I can see like a percentage. I'm looking at about the percentage of people that have voted. So we have about 74% that have voted. Give me another couple seconds here. Okay, we have about 76% that have voted. So I'll go ahead and close this down now. Okay, so it said 41% selected the first option. I have a good understanding of the model. 45% selected the second option. Oh, there we go. Tom, can you see any of that quick poll results there?
No, I can't, but I hear you.
Okay, so 45% selected the second option. I don't have a good understanding, but feel it's appropriate. 3% said I don't have a good understanding, so I'm withholding judgment, and 10% chose the last answer of I'm skeptical and it needs more critical information.
Okay.
Okay. So do you want to continue on before we launch the next poll?
Let's do, yes. Let's continue on a little bit, and I'll bring up the
All right.
Thank you, everybody, for responding. That feedback is important. So what I want to do now, what I've just covered was the process and the methods we used. And so we did this for all the species, for all the different conservation scenarios. And so now what I want to do is I'm not going to be able to show you all the results from all the species, obviously, but I want to pick a few results from the individual species to kind of illustrate some points. And then eventually I'll show you some final results where we compile across species to let you know how this process ended up in a decision. And so right here, what I'm showing you is for the prairie warblers. And these three graphs show you carrying capacity that's directly derived from habitat for our prairie warblers under the conservation scenarios, which are the different lines. And the three different graphs are the three possible climate change futures, essentially. And we have a current climate, a future that is modeled under a moderate climate change scenario, the middle one, the CGCM3, and then the GFDL climate change scenario is our most extreme scenario. And so what you can see here, rather than going through all these individual lines, what I want to basically capture is I want you to look at all the lines relative to the black and the blue. The black line is that baseline run with no restoration. The blue line is that random restoration. Everything else are versions of the landscape conservation design. And what you can see for prairie warblers here, for how their habitat responded, was that in general, the restoration scenarios all increased habitat and carrying capacity for prairie warblers, regardless of climate. Another thing you should note is that the GFDL scenario shows increases across the board, whether it's baseline runs and random runs. And what's going on there is that by the end of the century, we have climate change actually changing the forest structure to the point that it's actually providing some prairie warbler habitat. So that's interesting in its own right. So that's just habitat and carrying capacity. What about the populations? Well, first let me show you three different population models. What these show you is no conservation or restoration here. These are the baseline runs from the three different climate scenarios. And this just illustrates what we saw in the habitat models, or the carrying capacity graphs, that under extreme climate change towards the end of the century, we see the changes in the forest actually start to restore habitat to the point that the prairie warbler population starts to reverse its decline. So it's kind of interesting result in its own. But what happens when we actually simulate conservation scenarios? And you'll see these are population projections for the different conservation scenarios broken out by the different climate futures. And you can see here that in all cases, the black line and the yellow line here again are baseline and random. In all cases, the different versions of the restoration scenarios under landscape design dramatically improve the populations of prairie warbler. And under the GFDL, we saw populations even end up potentially above what they began at the simulation. Okay, but there's still a lot going on here. There's 3 different futures. One of the benefits of doing this approach with structured decision making in these models is that we can compile this across climates. So now we're pulling all results for different scenarios across climate models. So now we get one graph now that we can actually start to look at and say, on average, across climates, what's going on. And here, this just simplifies what we saw before, that conservation, that the landscape design scenarios truly benefit the prairie warbler population compared to not doing anything and compared to a random scenario. Okay, very good stuff. Good stuff to see. It's important to be able to see something like this. Okay, now this is still a lot of overlap between those individual scenarios. So if you were to make a decision based off of this, it would be very difficult. And that's why risk is so important here, is because now what we can do is we can take all that uncertainty in these error bars and stuff around these scenarios, and we can translate that down to risk. And now we get just a series of lines under the different scenarios. Again, the black line is the baseline, and we've got this blue line here, that's the random. And what this shows is for the prairie warbler population across all climates, what's the probability or risk of declining by a certain percentage over the next 2100. And what you can see is under the baseline scenario, obviously, there's the highest risk to the population. The other scenarios fall below that. So we've reduced the risk to the prairie warblers through these conservation scenarios. That's what it suggests. And now we start to see some separation. We can actually pick out what scenarios might be better because we're looking at risk. And now keep in mind that risk actually incorporates uncertainty directly. So we're accounting for that uncertainty here. These numbers are transparent and they're dispensable. So that's prairie warblers. Let's shift for just a second to wood thrush. Again, here's wood thrush carrying capacity or habitat. What we see is a different scenario. We see that conservation scenarios here all reduce carrying capacities of wood thrush. The black line is higher than the other lines, okay? That is because the restorations that are going on tend to focus on habitats that are less suitable for wood thrush. So, and this makes sense. Wood thrush are a general forest species, and most of the activity that's going on are woodland and glade restorations that are opening up those closed forests, right? So we see that wood thrush are negatively responding in terms of their habitat. But here, let's take a look at what happens in terms of the population. And here I'm just going to skip to where we look at the different scenarios under climate. And what you see is that even though wood thrush habitat decreased, the population projections under the different conservation scenarios, regardless of climate, are all nearly identical with lots of uncertainty. What this is saying is that even though the habitat was removed partially for wood thrush, the populations weren't affected by it. They still declined at the same rate. This is suggesting that there's other things going on, right? Probably fragmentation and parasitism processes that are affecting this population and not just habitat. Okay, so then what happens then is when we compare that prairie warbler risk to wood thrush, we can see that while one species definitely benefited from these conservation scenarios, wood thrush by and large were unaffected. That's an important ability to be able to see that distinction. So now we can say, you know what, we can focus on the results for this species, and maybe we're not as concerned about this species because it's adversely affected. Or we can capture both. Another really interesting result I want to point out right now is the brown-headed nuthatch model that we projected. What I show here are the responses to the conservation scenarios, and again, there's a lot of them going on. Just contrast the colored scenarios with the black line. And what you see is that these restoration scenarios that we did negatively affected brown-headed nuthatch in the region. They had higher abundances under the baseline scenario where we did no restoration, okay? the Ozark Highland team, when we worked through this, jumped on this, and they were very intrigued by this. And so we dug into it and looked at it. And here's what's going on. Brown-headed nuthatch are only located down here. They're limited to the southern portion of the Ozarks and the Boston Hills mainly. Okay? The restoration scenarios and the habitats being restored down here in this particular area were not the habitats needed by brown-headed nuthatch. Okay? Those habitats were mainly restored up here in the north, near the current River Hill subsection in the northern portions. Okay? That's where the habitat for brown-headed nuthatches was being restored. And you can see that here in the graphs. The line with the X's indicate the carrying capacity. You can see over time, we lost habitat and carrying capacity in the Boston Hills. As a result, the prairie warbler population, or the brown-headed nuthatch, sorry, declined. Up here, we saw increases over time in carrying capacity, but there are no birds there. And the dispersal limitations of these birds, they're a resident species that doesn't disperse very far. They simply weren't able to use that habitat because they weren't dispersing up there. And so the team jumped on that and they said, you know what, for the longest time we've been talking about reintroducing brown-headed nuthatch into other areas of the region. What if we could factor that into these conservation scenarios? And I said, we can, and let's do it. And so we just went back in this process and we said, for brown-headed nuthatch, for those restoration scenarios, not only are we going to restore habitats, but we're going to also reintroduce a small portion of birds in the first 5 years to the current River Hill subsection. And of course, when we did that, look what happened. Then we see restoration does benefit this bird, and we see the populations improve over baseline conditions. Okay, what I'm trying to get at here is the importance of being able to really dig into these processes and the benefit of a structured decision-making approach that lets you go back and change things when you find something out. Ultimately, in here in the last few minutes, I just want to finish up and show you we can produce these kinds of estimates of risk for all species, for all conservation scenarios, and that's what I show here. And what you can see is that in general, these different species on the left or on the right here, their risk was highest either under a baseline scenario or that random scenario. But within the rest of the landscape design scenarios, it really is quite variable. Species responded differently to these different scenarios, and scenarios were better for different species. So how do we come to a conclusion about what's best? Well, the team at the workshop decided to rely on the average risk across all species. Without any other evidence of having to weight species for any reason or not, they just wanted to average the risk across species. And so that's what we show here is the average risk of decline across species and across all climate futures. And what you see is that in one scenario does fall out. The scenario where we restored the full amount of acres on both private and protected lands based off the future prioritization was the scenario that the team would have picked. Now, I will point out that there isn't a lot of separation, right? The risk for some of these other scenarios is very similar, and we have to realize that that's just an artifact that most of these scenarios are actually very similar scenarios in any way. We're not looking at drastically different restoration scenarios. But nonetheless, the team actually had evidence and support to say that this was the best scenario, and they had a defensible, metric to say that. So that was really cool. And so that kind of captures the results. I'm going to present some conclusions, just a couple slides of what we really learned from this process as a pilot project. But before I do, I'd like to bring up the next poll, Yvonne, if I could.
Okay, I'll launch the next poll. Just the second question. This is the only other question. The question is, what is the most likely factor that would limit your ability to apply this approach to your own strategic habitat conservation? Is it the inability to pull partners and stakeholders on a team with a single goal, difficulty in determining the objectives or the metrics to quantify them, difficulty initially developing alternative scenarios to consider and the confidence that they could be realistic, the lack of data or models to access to expertise in producing data models to evaluate the scenarios, or all of the above. So I'll give you a couple moments to select your choices for that. So we have about 44% that have voted. Give you a couple more seconds here. More complex question, I guess. We have about 56% that have voted. Give you a little bit more time here. Okay, last chance. Okay, I'm going to close the poll. All right, so I'll share the results with you. So we have, for the first option, we have 36%. So the second option is again 36%, so those are pretty balanced. A little bit lower for the next one in difficulty developing realistic alternatives. That was 18%. Most of you chose, 73% chose, those numbers don't add up. It's odd at all. We'll have to look into why that's coming out the way it is.
Yvonne, they don't add up because people were allowed to select more than one response.
All right, okay, all right. 73% chose lack of data models expertise to produce the results, and 0% chose the last one, all of the above. So I'll hide those results and give it back to Tom.
Okay.
Thank you very much, people.
Thanks, Yvonne. Yeah. So what I want to do in just the remaining moments is just to present a few conclusions that the team and I were able to discuss and kind of pull away after all this process was done. We sat down in a workshop, and once we kind of arrived at this decision, we said, let's reflect back on this, and let's do so with respect to those three goals that I had presented in the beginning. And so some of the conclusions here. And that first one was, let's evaluate the landscape conservation design process that the team was piloting. And in general, I would say that that process was effective and necessary. We saw that compared to the baseline scenarios or the random restoration scenarios, that those other conservation scenarios under landscape conservation design all resulted in the species responded better to them. And so what that tells me is that this is definitely the case. Whether it's prioritization or the blueprints that the LCCs are looking at now, there definitely needs to be a strategy. It's beneficial. Secondly, was this idea, let's evaluate the dynamic landscape models and structured decision making. Does that framework, is it useful and insightful? Was it? And I think it was. First of all, we had a good reason that the team was able to come to a decision, and they could stand by that decision because there actually were numbers to support it. And one of the reasons they could do that was because by looking at risk and using it in a structured decision-making approach, they were able to kind of reach beyond that uncertainty and all that overlap and messiness, and they were able to kind of get past that. And then finally, one of the things that I hope I showed in those results was that, there was some important insight ecologically gained throughout this whole process. We saw things that might have been somewhat counterintuitive, but in hindsight, really told us a lot about how these populations are going to respond. And that's really important and helpful too. So I think this was a useful and insightful approach. And then for that last goal, let's prototype this process. I just want to take a couple minutes to do this real quick. And so at the end of this workshop, I sat down and I asked the participants, the team, especially the SWAP coordinators, I asked them, what did you think of this? What do you want to get out of this approach in the future? Okay, and what do you really want from this approach? And it was very interesting, the two responses I got. They were, I want to be able to know if I work on a COA, which is a priority area or a set of areas, will that help species? And which ones will it not? Okay. And then the other one says, I want to be able to identify the places to work on that will give me the biggest bang for our buck. And it was kind of funny because I thought to myself, those are what you want out of this in the future and stuff. And I really thought we kind of demonstrated we could do that, but maybe I didn't demonstrate that. And I got to think about it a little more, and I realized, you know what, we're not. And that's partly because those comments reflect the reality of the way the SWAP coordinators or planners have to work. They can't just simply lay out a long-term 100-year strategy and stick to it. They have to be opportunistic. They have to look at only certain areas at a time. They have to be able to work in costs and other things. And so there's going to be a lot of other stuff going on in their decisions. And what it made me realize is that recipe for landscape conservation design, it really, if it is a recipe, it's really coming down to two things. It's 1 pound strategy and 16 ounces opportunity. And that's not something that we showed in this pilot process necessarily. We looked at long-term strategy and how that would work, and that was great, but that really didn't help them on their day-to-day decisions, did it? And so what I would propose in going forward with this process is that there really is two different steps where this process needs to come into play in landscape design. And so if we go back and we say, you know what, we're doing landscape design. First of all, I think we need to realize that we need this process to help identify the strategies in general. What is the vision for how things need to be moved forward? These are big questions like private versus protected lands, how many acres in general, and how do we prioritize? The stuff that we addressed in this project. But at some point, their strategy is going to have to give way to actual scenarios or year-to-year or decade-to-decade plans that the planners are going to have to actually consider. And then at that point, we can come up with some scenarios and we can come back to this process, and these can be more concrete decisions then because we know those scenarios are realistic. That might ultimately get us to our sustainable landscapes. And so that's what I think this would be most useful. And with that, I'd like to finish up. If there's some time for questions, I will, but just real briefly, I'll acknowledge the GCPO for funding this project, the collaborators were Josh and Frank and Todd Jones-Farron with the GCPO. I'd like to thank the Ozark Highlands team for really kind of participating in this project and helping this process out a lot. I'd like to thank Greg Walton for his support and his input. And a lot of the work that we've done was really pioneered also by the Central Hardwoods Joint Venture. So I'd like to acknowledge them. And with that, I'll open it up to any questions via chat, or if people are allowed to speak, that's fine as well.
Thank you very much, Tom. You took an amazingly complex process and turned it into a very lucid presentation. I appreciate it. We have 2 written questions in the chat that you should be able to see, but since our audio does seem to be working well, I could probably let Jane Hines-Fry speak her own question. So I'm going to try and see. I'm going to try and unmute Jane. Are you there, Jane?
Yes, thank you very much. I'll just read off my question to you. Recognizing that this integration of models is a very complex process, could the general approach that you just outlined for us and showed the sort of general flow of the plan, could it be applied to different geographic levels, regions, states, cities, that are working on developing sustainability plans? In other words, could this process, can you imagine it being generalized?
Thank you, Jane. Thanks for that. That's a good comment and question. And I would say that was my intention and our intention all along, is that, we focused on developing specific models, but I really wanted to make this whole process generalizable and transferable to whatever setting happens. And that's part of the reason it was important for us to model things like bats and lizards, is because we have to show that we can get beyond birds too, and that we can address resident mammal species and so on. And so when it comes to population models and landscape models and so on, you're absolutely right. We can develop those kinds of models. If the data exists, we can develop those models for any species. And then it just depends on where the mapped information and so on are for those different settings like you mentioned. We actually have plans to just work with Missouri, and they've actually identified some of their own areas that they want to look at. And so we're going to work with Missouri and look at just the effects in Missouri too. So yes, that question is yes, and I hope it is.
Thank you.
Okay, another question we have here is from Rebecca Hammer-Lester, so I'm going to unmute Rebecca. Rebecca, you on? She may have stepped away. So I'm going to
go ahead.
Okay, you want to read the question for everybody?
I'll go ahead, yeah. So Rebecca asked the question, why does the population show such a crash in the first 20 years? Is that due to lagging conservation, balancing, climate change? So that's
Prairie Warbler, yeah.
Yeah, the prairie warbler. And, you know, we saw other species do that same response. Rebecca does a very good observation. Actually, what's going on there, as far as our model suggests, is it's not climate change. It's actually natural or background management and natural succession of our region. Especially for something like a prairie warbler, we continue to see a loss of early successional habitat in that woodland habitat, just from a lack of harvest and disturbance in the region. And so in the first 20 years, we really see that drop off, and it slowly starts to, that decline slowly starts to fade as the levels of management that we're simulating and the impacts of climate change start to kind of help raise habitat back up. So there certainly are several processes going on there, but that's been by and large natural succession and background management.
So I don't have any more written questions submitted. If there's anybody that would like to just ask a question, you could raise your hand and I'll unmute you. Well, I don't see any hands raised, so I just want to say thank you again, Tom Bonnot, and this recording should be available within the next day, and everybody who registered will receive an email. Oh, the other thing I wanted to do is I did want to upload the PDF of Tom's presentation that I am going to place as an attachment right now. So if anybody wants to download it right now, you can do that. But I will also be sending out an email to everybody with the link to the recording as well as a link to the presentation. Thanks very much, everyone.
Thank you, Greg.